Hi everyone. The today's session is on DFT and Z Transforms. The previous session, we discussed about the module one, that is discrete time systems and discrete time signals. The basic behind the discrete time signals and how they are classified, the operations on discrete time signals, and we have seen about discrete time systems, how it is classified based on its characteristics, and how we'll find the response of discrete time system for any arbitrary signal as input. And also, without input, if we know the characteristic equation of a discrete time system, we can find the solution or response of the discrete time system simply by solving the difference equation. And we have seen the stability concept and solving the system by using convolution and correlation we have discussed. Now let us move on to frequency domain representation of discrete time signals. Here in this module 2 we are going to discuss about the basic transform and important transform for discrete signals and also digital signals is discrete Fourier transform and also Z transforms. So let us see the basic behind transforms, Fourier transforms. So we know the Fourier transform for a continuous time signal x of t is x of omega, which is continuous and aperiodic. But if a discrete aperiodic signal, if we find the Fourier transform x of e power j omega, it is represented with x of e power j omega, because the formula x of e power j omega is sigma x of n into e power minus j omega. The concept behind this formula is any transform is calculated by multiplying the signal with the kernel of this transform. The kernel of discrete Fourier transform is e power minus j omega n. E power j omega t is the transform kernel in continuous case. E power minus j omega t is the kernel for a Fourier transform in continuous case. If it is a discrete case, we will multiply with the kernel e power minus j omega n. And instead of integration, we'll use summation as x of n is discrete. Hence, the discrete time Fourier transform x of e power j omega is equal to sigma x of n into e power minus j omega n. So the x of n is discrete sequence like any arbitrary sequence. It is an aperiodic sequence. The resultant x of e power j omega is a continuous. That's the difficult of using Fourier transform for directly for a discrete time signal. It is a continuous because e power j omega n upon n it will become continuous. E power j omega n is discrete, but for different values of n we'll get e power minus j omega. It is continuous with respect to omega. E power minus j omega, e power minus j2 omega, e power minus j3 omega. For any value of n, e power j omega is continuous with respect to frequency. So the frequency spectrum of a discrete time signal is continuous in frequency. And we know e power minus j omega is periodic with 2 pi. Cos omega minus j sin omega, which is periodic with 2 pi. So spectrum is continuous and periodic with 2 pi. Maybe from minus pi to pi, it's normalized here. Hence, if you find the inverse transform, it is as it is continuous, will apply integration, and it is periodic 1 by 2 pi 1 by 2 pi integration x of e power j omega and the inverse kernel e power j omega n d omega, right? But here why the name is discrete time, because frequency is not discrete, it is continuous. That's why it is called discrete time Fourier transform. If a continuous spectrum is given to a digital system or any discrete system, it needs an additional hardware to convert this continuous spectrum into discrete. That is, a sampling circuit is required. So we cannot directly feed this continuous spectrum to a digital system, because digital system will take only digital signals, or that is discrete signals. Hence, it has a drawback. Discrete time Fourier transform has a drawback that the spectrum is continuous, hence it is not possible to directly apply to a digital system for understanding the spectrum or to extract information from the spectrum. Hence, it is we are going for DFT. So DFT is nothing but the spectrum, continuous spectrum is sampled. Sampled version of DTFT is nothing but DFT. So we'll do sampling, and if you do sampling, here no need to do sampling by using a hardware. We'll do mathematically do sampling and we'll derive a transform called DFT. In the DFT transform, a new formula will be generated just by applying a sampling mathematically to the DTFT spectrum. What it will become when sampling to x of e power j omega. That means this x of e power j omega, this 2 pi period is divided into n samples, because this same period will be repeated in the next interval also, next period also. So we'll divide omega by 2 pi. E power j omega frequency is divided into samples. So frequency variable has to be sampled with a sampling interval of n, capital 1 by n, or you can say 2 pi by n, as it is 2 pi interval 2 pi by n is the sampling interval. Hence the formula will become sigma x of n into omega n power kn, omega subscript n whole power kn. What is omega n? Omega n is nothing but e power minus j omega j 2 pi by n. E power minus j, omega is replaced with e power minus j 2 pi by n. This e power minus j 2 pi by n is indicated with w subscript n, and that too here it is e power minus j omega. E power minus j 2 pi by n is represented with wn, and it is discrete. So a k is represented to a sample number, e power minus j 2 pi by n into k. E power minus j 2 pi by n into 0, e power minus j 2 pi by n into 1, e power minus j 2 pi by n into 2, and so on. Hence, e power minus j 2 pi by n is omega n, omega subscript capital N, the whole power kn. Hence, the formula becomes sigma x of n into w subscript n whole power kn, where wn is equal to e power minus j 2 pi by n, because 2 pi interval is divided by n samples. What is the range of summation? Summation is in the range from 0 to n minus 1 only. Previously, the summation is from minus infinite to plus infinite. For all the samples you want to sum. But here, no need to sample all the values, all the frequency. Because it is periodic, over the period of 2 pi, we'll do sampling. Same will be applicable for next period also. So 0 to n minus 1 or minus n minus 1 by 2 to plus n minus 1 will take from 0 to n minus 1 as a period. So n varies from 0 to n minus 1 x of n wn power kn. What about k? So k is also having n samples. For every period x of k having n samples. And what happens in the inverse? If you are doing the sampling of the spectrum, there is a provision that to do sampling in one domain, another domain will become periodic. Even though input signal is periodic and the spectrum is continuous and periodic, the continuous spectrum is divided into discrete by doing sampling. Hence, the time domain counterpart, which is aperiodic, will become periodic. Therefore, in the inverse also will vary n sigma k varies from 0 to n minus 1. X of k varies from 0 to n minus 1 and it is periodic. So 1 by n sigma x of k wn power kn. So x of n is also having only n samples. It is minus n because inverse kernel will use. So the formula is same. If you give input, spectrum will be calculated by multiplying input with kernel wn power kn. If the spectrum is given, the input is calculated by multiplying spectrum with wn power minus k. But it is 1 by n because it is periodic. It will become periodic. Spectrum becomes periodic. Over one periodic sample only we are calculating. So this is now the new formula. Both are discrete now and both are periodic. So in simple. So in the previously in discrete time aperiodic, for aperiodic signals only we will apply Fourier transform. For discrete time aperiodic signal, the spectrum is continuous and periodic. By sampling the discrete time domain signal will become periodic. So now both are periodic and both are discrete. That is called new transform by applying sampling in the frequency domain. That is called Fourier transform. Discrete Fourier, because this discrete here is only one term we are using for both time as well as frequency. Both becomes discrete. But previously discrete time Fourier transform, that means time domain only discrete but not frequency domain. So the discrete Fourier transform is applicable for both. Hence, the discrete Fourier transform is applicable for any periodic signal or aperiodic signal. Even if it is aperiodic, by doing discrete Fourier transform, it will become periodic. Right? So here also there is a chance of occurring aliasing. So you need to take care of choosing proper number of samples in the discrete in the frequency domain, so that when it is repeating in the time domain, it won't be aliasing, it won't be overlapped. Okay. So the conclusion is the discrete Fourier transform of a discrete time signal is discrete and periodic. Inverse discrete Fourier transform of any discrete spectrum is also discrete as well as periodic. Now, We'll see the properties of discrete Fourier. This properties of discrete Fourier transform is like similar like all other transforms. It is having linearity property, the frequency shifting property, time shifting. So this time shifting property is here mentioned with circular shift property because the signals are periodic. The periodic signals can be represented in a circular manner. So because it is repeating again, so if you traverse on a circle, the periodic signal again it will be repeated. So that's why it is called circular shift. And then frequency shifting and convolution. As we have a convolution in the linear scale, if it is an aperiodic signal, we can represent it as a linear convolution. As two periodic signals are convolved, then it is called circular convolution. And then conjugate symmetry. So for the symmetric property of DFT is very much useful to reduce the number of computations. Next one is Pascal's theorem to find the energy of the signal in both time domain as well as frequency domain. And then time reversal signal. So let us see the property conceptually. Instead of deriving this property, how we can understand these properties conceptually so that mathematically it can be derived. So linearity property. So as we know, linearity property means superposition. If a combination of two signals is applied with DFT, then their individual DFT is also combined. So AX1 of n plus BX2 of n is the signal applied for DFT. The signal is applied to DFT transform. Then its transform is AX1 of k, capital X1 of k is transform of X1 of n, and X2 of k is transform of small x2. Both are combined as well as multiplied with the corresponding constants. It is linear because sigma x of n e power j omega n kn or wn power kn, it is separable. As it is sigma, it is separable, so it is possible to satisfy superposition principle. Next one is circular shifting. So if we shift the signal, it is represented with x of n minus m, but it is circular shift, it is subscript capital M. So rotation, so here shift is represented with rotation. So, rotate right side will indicate shift right. So that means clockwise. Rotating a signal is represented in a clockwise is equivalent to right shift of it. If you do rotate the signal the left side or in the anti-clockwise direction is equivalent to left shift of the linear scale. So we know the shifting operation in any transform. If you shift the signal in one domain, then another domain, the spectrum will be multiplied by kernel. So what is the kernel here? E power minus j 2 pi by n into kn. Here it is represented with wn power kn. This kernel is wn power kn. W is e power minus j 2 pi by n, which is a Twiddle factor. So here we are shifting x of n to m. So spectrum x of k multiplied by w n power kn. So n is replaced by m. N is shifted to m. So in the kernel wn power kn, n is replaced with m because n is shifted, time domain is shifted. So wn power m into k multiplied by x of k. So we have to remember this thumb rule. When the signal is shifted in one domain, another domain will be multiplied by the kernel. Similarly, frequency shift. So x of k is frequency domain spectrum. This frequency domain spectrum is shifted by L times circularly. because subscript n indicates a circular shift. If we shift the signal circularly in the frequency domain, then time domain will be multiplied by kernel. What is in the frequency to time domain? Kernel is opposite kernel, Wn power minus kn. Here k is shifted to L, so in kernel k will be replaced by L. So W subscript n whole power minus Ln is the kernel we want to multiply in the counterpart domain signal. So counter to frequency is time, x of n into Wn power minus Ln. That's the property of both shift in time as well as frequency. Next, circular convolution. When you do convolution between two signals, x1 of n, circular convolution is x2 of n, its transforms are multiplied. Convolution in one domain leads to multiplication in another domain. Here, star n circle indicates circular convolution. Okay. So this is simply convolution in one domain is equal to multiplication in another domain. So frequency convolution also is possible. If you convolute two spectrums, then their input signals, then the corresponding time domain signals are multiplied. So, but it is in the reverse direction. Inverse direction means 1 by n will get 1 by n into x1 of n into x2 of n is equal to x1 of k convoluted with x2 of k. Right? That is convolution both in time domain as well as frequency domain. The next one is conjugate symmetry property. So this is very important. Conjugate symmetry property. X of n is a real signal, not a conjugate signal. Then its spectrum is x of k is equal to x star of n minus k, capital N minus k. That means it is folded and shifted by capital N. So if you find half samples of the spectrum, we can find the remaining half samples by using x star of n minus k. If you know x of 0, then it is equal to x of n minus 0. When k is 0, x of 0 equal to x of, let it be n point, n is equal to 8, then 8 minus 0. So x of 0 equal to x of 8. X of 1, k equal to 1 means x of 8 minus 1, x of 7. Similarly, we can calculate half of the values if we calculate, remaining half can be easily derived from this property. And another important thing is Parseval's theorem. So Parseval's theorem indicates that if you find the energy of a signal in time domain, that can be equal to energy of the signal by using the spectrum also. So energy of the signal x of n is sigma x of n square. Similarly, energy of the signal in frequency domain x of k square, sigma x of k square. It's 1 by n sigma x of k square. That is Parseval's theorem. Next, time reversal. So as we know, time reversal means if you reverse the signal, the spectrum is also reversed. That means here generally signal will be reversed, but here it is complex conjugated. Complex conjugated of the transform x star of k. Next, circular versus linear convolution. As we told, circular convolution versus linear convolution. In circular convolution, both the signals must be periodic, and also the length of the both signals must be same. That means both the signals must have same period. The length of x1 of n must be equal to x2 of n. If the lengths are not equal, then we want to add additional zeros to the sequence which is having less length. That is, if x of n is having length L1 and x1 of n is having length L1 and x2 of n is having length L2, then the length of the circular convolution is equal to maximum of L1 comma L2, which is having highest length that will be considered. The lowest length sequence will be converted into same as highest length by simply adding zeros, additional zeros at the end of the sequence. But in the linear convolution, the sequence lengths may not be same because it is not periodic. It is can be aperiodic also. The linear convolution is applicable for both periodic as well as aperiodic. If the length of x1 is L1 and length of x2 is L2, then the linear convolution length is L1 plus L2 minus 1. The length will be increased. But whereas in circular convolution, both the sequence lengths are n, its output circular convolution sequence is also equal to n. Signal length will not be changed even though if you do the circular because it is periodic. Okay? So there is circular convolution versus linear convolution. So this jet DFT, discrete Fourier transform, is very much essential in implementing Fourier transform in digital hardware. The digital hardware can be used to perform this Fourier transform with the help of this DFT procedure. The next one is jet transform and region of convergence. What is jet transform and its region of convergence? So jet transform is equal to the formula for jet transform is similar to the all the transform. The signal multiplied by the kernel. X of n sigma x of n into z power minus n. Whereas the DTFT Fourier transform formula is also same as like this. X of e power j omega equal to sigma x of n into e power minus j omega. So what is the difference here? The z is replaced with e power j omega. The e power j omega is replaced with z. So this is the relation between DTFT and z transform is x of e power j omega equal to x of z and z is replaced with e power j omega. But actually z, the formula for z is equal to, the general formula for z is equal to r into e power j omega. So it is a unit circle. Z is a z plane. In z plane, the regions are divided with circle with different radius. So r into e power j omega, r indicates radius of the circle, omega indicates angle. So here z is equal to e power j omega means r is equal to 1. That means z transform is equal to Fourier transform evaluated on unit circle. Indicates evaluated on the unit circle. But why we are moving from discrete Fourier transform to jet transform? It is also discrete case only. But what is the need for going for jet transform instead of using Fourier transform? There is a condition for Fourier transform to exist. To calculate Fourier transform of any discrete time signal, it must be absolutely summable. Must be absolutely summable. Then only it is possible to find out Fourier transform. Or we can say it is energy signal. The energy of the signal must be finite. Or we can say absolutely square summable. Because the formula for energy of the signal is sigma x square of n. Since if it is absolutely summable, its square should also be absolutely same. Then it is called finite energy and finite energy it contains. If it contains finite energy, then we can say it is an energy signal, right? So if the signal is not an energy signal, then the, the summation, DTFT summation will become infinite. Sigma x of n into e power minus j omega. X of n is not a bounded signal. It is not a finite energy signal. At that time, then you can say it is not possible to find out Fourier transform for this one. So to convert the unbounded signal into bounded, so just we will multiply x of n with a decaying signal, exponentially decaying signal. What is the exponentially decaying signal? Some a power minus n. So a power minus n is nothing but exponentially decaying signal. That is indicated with r power minus n. So Fourier transform x of n into e power minus j omega. This Fourier transform x of n into e power minus j omega. X of n is not bounded signal. Then x of n must be multiplied by r power minus n. So x of n into r power minus n into e power minus j omega is nothing but r into e power j omega whole power. But r into e power minus j omega is nothing but z. That is equal to this. When it is equal to Fourier transform means when r is equal to 1. This is the concept behind Z transforms. How the Z transform is derived from the discrete Fourier transform. And we'll see that r, it is not even if you multiply with r power minus n, it may not be possible to convert it into finite. It is possible to convert that summation into finite only for particular values of r only. The sigma r power minus n into x of n may be a bounded signal, maybe become a bounded signal for particular values of r only. It may not be possible for all values of r. That is called region of convergence. So mod z, so mod z may be greater than some r1 or mod z may be less than some r1, or it may be between two radiuses r1 and r2. So that depends on the signal type. So ROC is nothing but the region of the Z plane where the Z transform is finite or the Z transform exists is called the region of convergence. So if you see some of the signals and a region of convergence, the right-sided signal, or we can say causal signal, the signal is finite for the positive instance of time. That is called right-sided signal. It is 0 for the negative instance of so causal sequence. So for causal sequence, x of z is exists only for mod z greater than r1. So the example is a power n into u of n. So if mod z greater than a, it is possible to find out rate z transform. But for the left-sided signal, it is possible to calculate Z transform only for mod Z less than R2. That is, for example, minus a power n, u of minus n minus 1. So u of minus n minus 1 means u of n is right-sided signal, u of minus n is purely left-sided. We will reverse it. It is purely left-sided signal. It is left shift by minus 1. So it will not, it won't start from 0. It starts from minus 1 to minus infinite. Minus 1 to minus infinite means completely negative side or completely left side. So it is left-sided signal means it won't include origin. For left-sided signal, the ROC is mod z less than. Similarly, two-sided sequence. If it has some samples in the positive instance of time as well as some samples in the negative instance of time, means the Z transform exists in a ring, in a combination of two radiuses. So R1 to R2, not Z greater than R1 and less than R2. And this is for infinite durations, all right sided, all left sided, or between both right side and left side. So two-sided sequence. What is finite duration sequence? Finite duration sequence means if it is having finite duration sequence, it is having entire Z plane except Z is equal to 0 or Z is equal to infinite. Depends on the right sided or left side. If it is right sided finite duration sequence, then it is possible to find Z transform for all values of Z except Z is equal to 0. Because formula x of n to Z power minus n. When it is right sided, n is positive, Z power minus 1, minus 2, minus 3 and so on. When Z is equal to 0, so Z power 0 power minus n means it is 1 by 0, it is infinite. 1 by Z power n. Z is 0 means 1 by 0 is infinite. If it is purely left-sided finite duration sequence, means it is possible to find Z transform for all values of Z except Z is equal to infinite, because we will get all the positive powers of Z. Likewise, you can find the Z transform for any input signal, but for few kind of uh, for the limited region of convergence. That depends on the signal. So, but the region of some convergence has some kind of rules and regulations. Those are it must not contain pole. Within the ROC, it does not contain any pole, and it may be connected ring or disk or above it, below the region of convergence also. So based on the region of convergence, we can determine the signal time. If it is greater than some radius, it is causal signal. If it is less than some radius, we can say anti-causal signal, because purely left side like this. So as like DFT, Z transform is also having properties. So the same kind of properties, but so little bit change in the kernel, as the kernel is changing, but it is not periodic. We will get a different kind of properties. So as we know, the same kind of properties: linearity, time shifting, scaling property, time reversal, convolution, differentiation and correlation. So linearity property means again the superposition concept. If it satisfies the superposition principle, then uh, it, it is easy to find out the transform for a combination of multiple signals. So if you know the individual transforms, you can find the for a complex signal just by simply adding the signal spectrums and multiplying with the constant. Time shifting property. In the time shifting property, if we shift the signal, same concept, if we shift the signal in one domain, spectrum will be multiplied by the kernel. So here kernel is Z power minus n. So x of n minus k, as n is shifted to k, so x of z is multiplied by kernel. So kernel x Z power minus n, but n is shifted to k, so it is multiplied with Z power minus k into x of z. In a similar manner, if you shift the Z domain signal in the frequency by some Z naught, x of z minus z naught means the input signal will be multiplied by the kernel Z power minus k into x of z. Here, next one is scaling. Uh, the signal is frequency domain scaling, or input multiplied by exponential sequence. When input is multiplied by an exponential sequence a power n means, then the z domain will be scaled x of z by a. Okay? If a is greater than 1, then the spectrum will be expanded. If a is less than 1, the spectrum will be downsampled. And time reversal signal. When we reverse the sequence or the signal, then the x of z will be again scale. So x of 1 by z. And similarly convolution, when you do convolution in one domain, multiplication in the another domain, then x1 of n convolution with x2 of n is nothing but multiplication of its spectrum x1 of z into x2 of z. And multiplying here, the most important property is differentiation property. In solving the continuous differential equations, some analog systems, its characteristic equation mostly in the differential equations, not like unlike digital system, their characteristic equations are difference equation, linear constant coefficient difference. But for analog system, it is linear constant coefficient differential equations. So it is necessary to use this differentiation property in the Z transform. What this differentiation property says, so when you differentiate the spectrum with respect to Z, then the signal will be multiplied by its n. So time index in the time domain. So n into x of n leads to dx of z by dz and multiplied by minus z. And similarly correlation. So we know that convolution and correlation are similar, except there is no folding in the sequence of in the mathematical operation. In the convolution, as we have described, the x of n is one sequence and h of n is another sequence. In convolution, one of the sequence kept constant and another sequence has to be folded, and then shifting from minus infinite to plus infinite, wherever the samples are matched, there will multiply for every shift operation. But in the correlation operation, when you do correlation, the same kind of operation as that of convolution, but instead of folding the sequence, just will shift the sequence. The one of the sequence kept constant, another sequence without folding, it will shift from minus infinite to plus infinite. For every shift, it will be multiplied with the another sequence. That means it is equivalent to convolution when the input signal, one signal is as it is, another signal is folded and then applied convolution. The x1 of n is one sequence, x2 of n is another sequence, x1 of n and x2 of n. In convolution operation, will fold and will shift, but in correlation won't fold. So how we can make correlation as a convolution means perform convolution operation, that means fold the sequence and then convolve, shift the sequence. If it is equal to correlation when you do convolution for a folded sequence, one sequence with a folded sequence. Already the input is a folded sequence. During the convolution operation, the folded sequence again folded means original sequence. So convolution of x1 of n multiplied with x2 of n means x1 of n kept constant, x2 of n is folding and shifting. If you take second sequence already folded, and if you do convolution means folded signal again folding means original sequence. So original sequence is shifting from minus infinite to plus infinite and we are multiplying means then it is equivalent to convolution. So that's why the correlation is indicated as x1 of n convolution with x2 of minus n. That is the folded version of second sequence. Then its Z transform is, that is, convolution in one domain is equal to multiplication in another domain, x1 of z into x2 of z. But what is x2 of n? It is reverse signal. If you do reverse, what happens in the spectrum? It is inverse to the z transform. X of x2 of 1 by z. So x1 of z multiplied by x2 of 1 by z indicates the z transform of correlation. Similarly, you can find out the Parshall's theorem also. So you can find out the Parshall's theorem here also, and initial value theorem and final value theorem. So the next one is inverse Z transform. We know the inverse Z transform formula. As we know, the inverse Z transform is integration of x of z into z power n minus 1 over 1 by 2 pi. So over the residue we want to calculate. So it can be calculated directly by solving the integration of x of z, or it can be calculated by using some methods. So the first method to calculate inverse Z transform is partial fraction expansion. Second one is long division or power series method. Third one is, as we discussed, the integration method. This can be done by finding the residues of x of z into z power n minus 1. So the partial fraction method, the x of z is divided into, Z transform is divided into sum of subtransform. We'll find the roots of the denominator and we'll represent as a sum of subtransfer functions. You know the sum of subtransfer functions, smaller order transfer function. We can directly apply the inverse Z transform, because Z transform of u of n is equal to z by z minus 1. If you have any polynomial, if it is divided into, splitted into subtransfer function, z by z minus 1 plus z by z minus 2 like this, then we can represent it as u of n, a power n into u of n. So that is one kind of, so we are reducing into smaller order transfer functions. That can be directly calculated in the inverse Z transform. Another one is power series method. Power series long division method will divide the numerator by the denominator in negative checkbox. So, and we'll calculate the coefficients for x of n. So that coefficients will indicate directly the input sequence, delayed sequence, and the residue or contour integration. So to do all this Z transforms, we must need some basic Z transform of basic signals. So the basic signals Z transforms are, you know, the basic del of n unit impulse and unit step sequence and the exponential sequence. And more particularly, as I told, the differentiation property. So if you multiply signal with time n into some signal, then its spectrum is differentiated by z. So this is very much essential in finding the z transform. So z transform of del of n is 1. Z transform of u of n is z by z minus 1. So a power n to u of n is z by z minus n. So as it is multiplied by n means it will be differentiated. So u of n is z by z minus 1. If you multiply u of n with n means the differentiation of z by z minus 1 leads to z by z minus 1 whole square. So similarly, if you multiply a power n into u of n means, so with n means a power n to u of n z transform z by z minus n. We'll apply a negative minus z into d by d, dz of x of z. Like, so you get that. So So similarly, cos omega into u of n is sin omega into u of n. So we can't directly calculate it. We have to represent using Euler's formula. So cos omega naught n or sin omega naught n are represented with the Euler's formula. That is, cos omega naught n can be represented as e power minus j omega plus e power minus e power j omega plus e power minus j omega. So negative means the negative part will cancel. Only will get cos omega. Similarly, if you subtract e power j omega minus e power minus j omega means cos term will get cancelled with its sign. So e power minus j omega means it can be calculated by using a power into u of n formula. So if we minimize it, we'll get finally this. This is transform. So for now, if we come to transforms, if we come to systems, how can we represent the systems in the frequency? So far, we have discussed how the signals are represented in frequency domain by using DFT or Z transform. That depends on the domain, continuous and discrete. So even for a discrete case only Z transform is used, but whenever Fourier transform fails, we go for a Z transform. So anything, both are for discrete case, Z transform or DFT. So now coming to the systems, discrete system. So any discrete time system can be represented with the frequency domain with the help of transfer function. What is transfer function means? H of z is equal to transform of output by transform of n, y of z by x of z. So it is a polynomial, it may be a polynomial, and this polynomial has numerator polynomial as well as denominator. It's a ratio which is having polynomials in numerator as well as denominator. We can decide the system stability and some characteristics by using the roots of this numerator and denominator. The denominator roots indicates poles of the system, the numerator roots are indicates zeros of the system. So based on the pole location, we can decide it is a stable or unstable system. So in a discrete case, the unit circle will be considered for the stability criteria. All the poles lies within the unit circle, then it is stable. So all the poles lies outside the unit circle, or at least one pole lies outside the unit circle, means it is unstable. And if all the poles are on the unit circle, means it's marginally stable. So this roots of the denominator is very much essential to determine the right stability of the system. As I told, all the poles lies left side within the unit circle, it is stable system. All the poles, this is right side, outside poles, this is inside poles, and some poles which are on the circle also, and it is marginally stable. It is on the, it is completely outside the unit circle means then it is unstable. So the overall summary of this transforms is mostly the Z transform and DFT. So how DFT is derived means from the basic Fourier transform, DTFT. So this DTFT of any discrete system is x of e power j omega, which is continuous in omega, but it is periodic. So that continuous term will be converted discrete. So it will be x of t. Z transform is if DFT or DTFT fails, it will go for Z transform. By using Z transform, we can represent any system also in terms of y of z by x of z as a transfer. We can find that stability of the system with the help of transfer function roots, that is numerator as well as denominator. So if we know that Z transform h of z is replaced with e power j omega, and if we vary the omega, and we can find out the magnitude of h of e power j omega, so that we can see the shape of the transfer function. That is how the system characteristics is varying with frequency, which is very crucial in filters. So if it is low pass filter means how it is varying with frequency. Beyond some cutoff frequency, it becomes zero. Below that cutoff frequency, it is high. So we find the response of the system with respect to frequency is very much essential in all the systems. Okay, so this is overview about the uh, transforms. So most important thing, next module we are going to see for fast Fourier transform. So fast Fourier transform is a method to find out DFT. An improved better method to find out DFT. That means DFT or Z transform, everything is a computation sub sigma you need to find out. So this summation is nothing but summation of products, sum of products. Here the computations are nothing but addition and multiplication. And n samples may be there for example. So in kernel also having n samples. N into n multiplications it may require. So n square multiplications is required. And if the signal is a complex signal, and this spectrum is also this wn power k, kernel is also e power minus j omega. So it is also complex. If x of n is complex signal, then this n square multiplications needs again internally 4 multiplications for performing multiplication of two complex. So 4n square number of multiplications it requires, and it needs addition of 4 terms to calculate one multiplication again. So it needs more number of calculation if the signal becomes complex. So for higher values of n, again this complexity rises, improves. So it will not be efficient for performing Fourier transform for real-time signals, because n value is very high and it needs more number of computations. So to reduce the number of computations, it needs to develop a new algorithm by using this property of the two-deal vectors. So it has a property that it has periodicity and symmetric property. That's what we are going to discuss in the upcoming modules. So that is fast Fourier transform. So with the help of its property, less number of two-deal factors, we can find more number of computations. We can find more values without higher computation. We'll discuss this module 3 as Fourier transform for finding DFT using fast Fourier transform. This it is very important for finding any like in MIMO and even in image processing, two-dimensional signals also. It is the Fourier transform is calculated by using the FFT algorithm, fast Fourier transform. And so many fast Fourier transforms as well based on the radix 2 and radix 4 and the split radix 50. So many variations as developed to improve the speed and as well as to improve the area, sorry, to optimize the area, the power consumption and all. So the main concern is speed of the system. The speed of the system, the computation should be more. So speed of the computation should be more means within the less number of computation we want to achieve more output values, more samples you want to achieve. That can be possible by using a specialized algorithm called fast Fourier transform. Fast Fourier transform is not a transform. It is a efficient way of calculating DF, discrete Fourier transform. Thank you. So the quizzes are available in the website. take the quiz, and after taking the quiz, you can see the solutions, and explanation is given for each and every quiz. Every module contains a quiz, and also it has a study material, lecture notes, handwritten lecture notes. You can go through this lecture notes for the derivation problems, and you can watch these videos for the conceptual clarity. So most of the concepts, the links between the topics will be explained here, and you can practice by using quizzes and study material. Thank you.